Hi, welcome and thank you for joining part three of the technique series on dynamic light scattering. My name is Julie Chen Nguyen, and I will be your facilitator today. Dr. Jeff Bodycomb, our product line manager for particle characterization, will be your speaker today. Jeff has a wealth of experience on nano and subvisible particles. So we'll have a chance at the end of the webinar and a Q&A session to pick his brain or ask any questions that you may have regarding DLS or NTA. Jeff, I think that's about it. When you're ready, would you please share your screen?
All right. I'm Jeff Bodycomb. I'm with Horiba Instruments in the Particle Characterization Group. And today I'm going to talk about part three of our series on modern particle characterization techniques and dynamic light scattering. So quick outline of what I plan to do. We're going to go through an introduction, kind of do some introductory comments around getting you ready to talk about the technique and some perspective. And then I'll talk about what is dynamic light scattering and what exactly do you measure, which kind of tells you what results you get out. And finally, I close with a discussion on some ideas in method development, because a lot of the excitement in DLS comes from getting the sample ready to put into the analyzer. And so you'll want to have some thought into that. Quick word from our sponsor, if you will. Did you sign up for our newsletter? So if you let us know, we will send you a regular update about once a month with upcoming webinars and news on the world of particle analysis, which everything from Horiba events to classes, short courses that seem to be of interest to the particle community. So if you're interested and you don't already receive it, go ahead and send us a chat or email your desire to us at labinfo@horiba.com. So kind of opening question, what is dynamic light scattering? So dynamic light scattering really refers to measurement and interpretation of light scattering data on a microsecond time scale. And the time scale is important because we're really looking at things like particle molecular size or size distribution and relaxations in complex fluids. And if you went to much longer time scales, you could also talk about some dynamic, some particle growth questions and so on. Other techniques, if you start thinking about measurements with durations of over about 1/10 of a second, that's static light scattering or laser diffraction. Julie is moderating today, but she's expert in that area. Used for determining particle size for diameters greater than about 10 nanometers, polymer molecular weight, second virial coefficients, radii gyration. So there are various applications, and they all come with different names. Electrophoretic light scattering, which will be really using the Doppler shift in the scattered light to probe the motion due to an applied electric field. And that's for finding electrophoretic mobility and zeta potential. We are going to have a talk about that later on in the series. And finally, nanoparticle tracking analysis, where you use scattering to track the location of a particle as a function of time. That is really particle motion, and then you use the motion to determine particle size. I like to put up a graph. Along the bottom, I have diameters in microns, and on the left, I have resolution of mixture components. So if you wanted to separate materials, you move up on this y-axis. And we're really operating in this range from sub-nanometer scale up to about 10 microns. And now there's some squishiness, and I'm going to get to that as we get into the meat of this talk. So before we go on, I want to mention what is laser diffraction. So laser diffraction, you see an image on the left where we shine a beam of light onto a sample, and then we look at scattering as a function of angle. Works well for sizes up to 5 millimeters now. And so we convert the scattered light to size distribution. It's very fast, it's very repeatable, and it's very popular because of the wide size range, repeatability. And you can use it with both suspensions in liquid as well as dry powders. Some example results, kind of going from the bottom end to the top end of size scales. So you can do, say, a colloidal silica suspension with about a 30 nanometer diameter. And you can also look at things like coffee, sizes going up to over 1 millimeter. I wrote 1 millimeter here, and I look at this graph and realize that I have sizes pushing 3 millimeters in the results. So there you go. And nanoparticle tracking analysis is another scattering technique. This also is used with nanoparticles, like dynamic light scattering, but the approach is somewhat different in that we have light sources, here shown on the right, illuminating a sample, and then we use a video camera to collect videos as a function of time. And so what we're really doing is we have the light source coming in from the left side here. You have a particle moving around about at random by Brownian motion. And then you have a microscope and a camera filming the location with time. And so you'll extract a motion for each individual particle, and then you'll extract the size distribution by looking at lots of particles. So you're like a video with a number of particles in it. So those are some introductory comments and some perspective on related techniques. And now I want to move into what is dynamic light scattering and what exactly does it measure. The optical system is pretty similar to nanoparticle tracking, except I put the laser on the left instead of the right, but the laser is coming in here. I have particles, and then I'll have a single channel detector, in this case either at a right angle or a backscatter, and then I'm going to collect the signal as a function of time. And the signal, as I've shown in this upper right corner, if your system is built properly, looks very, very noisy. And that noise actually comes from particle motion.
Just place the cell in the analyzer, click on your method, the measurement begins, and then results are displayed and may be printed in easily custom.
Okay, so basically in that video, you saw that the procedure of measurement is fairly straightforward in that once you have a sample, you stuff it in the instrument, you press go, and there's your answer. And that's part of why this talk is going to be so weighted towards method development discussions, because it's getting the sample into the cell that can be the most exciting. I want to comment on Brownian motion. It's used in dynamic light scattering and in nanoparticle tracking analysis. It is tolerated in zeta potential analysis. Basically, particles in suspension, they're small, and they undergo a random thermal motion. And there are a couple ways to look at it. You can say it's thermal energy divided by viscous drag. It's usually how I like to think about it. You could also say it's just being kicked about at random by molecules of solvent. So the nice thing is that it's related to particle size. That's what I want. It's related to this liquid viscosity, which is often or something I already know, and related to temperature, which is typically something I control. There's a sketch of some particles moving about, and the larger particle just moves more slowly than the small particles because of the larger viscous drag of the large particle compared to the small ones. So the DLS motion, DLS signal rather, is, like I mentioned before, is random. So it's just fluctuating up and down. And this is happening because the particles are moving about randomly with respect to each other. And so you have scattering for each individual particle interfering constructively or destructively. And as they move, you'll have different amounts of interference. Your signal fluctuates up and down, and it looks like noise that is really due to your experimental system and not due to electronics or laser or any other thing like that. One way of looking at noise is to calculate what's called an autocorrelation function, which is really a measure of the relationship between a signal at some initial time and some later time. And as you can imagine, if you look at the signal at some particular time and you look at it a very short moment later, nothing much changes. That would be a high autocorrelation. And if you look at the signal at some initial time and you wait a bit and you look at it again, they could be quite profoundly different. And so that autocorrelation will tend to go down. I have lots of equations in here. Just let you know that it's all in the software. So unless you want to impress your friends at light scattering parties, you don't need to memorize them or anything like that. Effectively, what we want to get out is some sort of decay constant, because this will show an exponential decay. So that's that gamma. That gamma is related to the mutual diffusion coefficient, or how the particles move with respect to each other, and q squared, where q is the scattering vector, and that's a description of the instrument geometry. So it's sine of the scattering, half the scattering angle, refractive index of the liquid, and wavelength of incident light. And this is a nice, scattering vectors are a nice way to collapse all your scattering equations into one form, whatever radiation you're using. You can relate hydrodynamic size to mutual diffusion coefficient through the Stokes-Einstein relationship, where you have a thermal energy term on top, swap size and diffusion, and you'll get a viscous drag on the bottom. Note here, I wrote viscosity because it's a stiff function of temperature. And really the take home from this slide is that you do need to pay attention to sample temperature, mostly because of the viscosity term, and that has some practical implications for measurement. And that practical implication, of course, is that you don't take a sample out of the fridge, put it into a 25°C instrument, and get the right answer because the liquid is still cold and warming up. Now, this is probably the most important practical slide, except for my comment on temperature, for dynamic light scattering, which is what is hydrodynamic size? So we report a size by DLS, and it's really the diameter taken from viscous drag, and it's the diameter of a sphere that moves or diffuses the same way as your sample. So if we all went through life with billiard balls or simple hard spheres, there will be no further discussion, and this will be pretty boring. What's more likely to happen is that you'll see particles that are core shell particles, like shown on the left. So you might have a solid core, and then you might have a hairy shell. Now, what happens if you have a bunch of small particles that are stuck together quite firmly, and you have some sort of aggregate, or even a agglomerate that's loose? I'm going to report the size by DLS of that group of particles. And so if you have aggregation happening in your system, you're going to go out and measure the size of your aggregates. Quite often this is useful because if you're after particle size, you kind of want to know what your entire unit is. There are a few edge cases where it's more important to actually know the size of the piece of the aggregate, and DLS is probably not your friend there. But the most common cases, DLS works, as long as you're aware that you could be looking at aggregation phenomena. And finally, I've mentioned billiard balls, so I guess the next sports analogy will be a football. So if I had a football-shaped particle or a rod, then I'm going to report the size of a sphere that moves the same way as the football. Now, somewhat irritatingly, as I report neither the length or the diameter of a football or a rod, I report some intermediate value. But again, this is one of those things, as the particle gets bigger, you'll see larger sizes. And if you're aware of this is what is happening, then it's fairly easy to reconcile results from different techniques and not get too distracted. Yeah, but it's very important to keep in mind what you're looking at when you try to compare your sizes or understand your chemistry. So some comments on hydrodynamic size and examples. These are gold colloids. This was some analysis at NIST, and so they did various kinds of microscopy, and then they did dynamic light scattering. So if you look at an electron micrograph of a gold colloid, you will see the metal core. So here we're seeing a size of 10 nanometers or 9 nanometers by electron microscopy, but DLS is giving us 13.5. So why is this? It's because the gold nanoparticles are stabilized generally by citrates, and the citrate does not have a high electron density, and so you don't see it in electron microscopy. And so basically what you do in electron microscopy is you'll see the gold core, and if you don't dye or label the citrate, you might miss it. Modern, I should say newer electron micrographs are much better, but the lesson remains, if you have a core shell particle, you look at everything, even if you can't see it with other techniques. So here's some nano gold data from us, and I show here really a autocorrelation function. So on the left side, you see it starts high and it decreases down and sits down to around the baseline. And I have repeats of the Z average size, which I'll get to soon. And I'll have an average of 50 nanometers, standard deviation 0.9, not with the distribution, but repeatability of measurement, and a coefficient of variation of under 2%. So contrast that with some 10 nanometer gold. So that's shown in the autocorrelation function, the second one down. So the one on the top is from the previous slide. So as you move your eye down, you'll see that the smaller gold particle has the autocorrelation function start going down more quickly with a short delay time. And that really says the system is just moving around much faster, and the connection from time to time is a little bit weaker. Well, that's because they're small particles. They like to run fast. And so you'll obtain, in this case, it's a 10 nanometer nanoparticle. Coefficient of variation is still about 2%. So this is a quick overview of how to look at autocorrelation function as they shift to the left. That means that your particle sizes are going smaller. The position also depends on your scattering angle and viscosity. If you remember, shifting left goes smaller. That's fine. If you forget, the software does it for you. So comparison between labs. So this is colloidal silica measured at two different laboratories, two different analyzers, 34.4 and 34.6 nanometers. So on z-average sizes, we do quite well between labs. Again, this course requires that both labs have the same sample, that we don't have any splitting effects. Generally, those don't get to us with nanoparticles because they're small and easy to mix. So anyway, this is a technique that can be done in multiple sites and reconcile the results. Another example measurement, here's polystyrene latex. This is a narrow standard, and in this case we had 105 nanometers, which is exactly what we expect. Now, of course, latex are used commercially in a number of applications, and they are not nearly as well behaved. That said, a lot of latex polymerizations are controlled with dynamic light scattering, because you can use it to look at the emulsions as well as the final product, and it's in the right size range. So I mentioned commercial latex emulsions, and the range of sizes is not always so sharp and narrow as you see in the standards. And what we do with that is use the method of cumulants. So when I started talking today, I cheerfully told you, hey, there's one exponential decay, and that was this equation up here. Now I'm saying, well, we have a bunch of different sizes, and one way to look at it is to say that our exponential decay really looks like a power series. This is called cumulants. Again, software does it for you. If you want to look it up, you'll look at Koppel has a discussion. So we're going to report, instead of just the size, some sort of an average size, and that's called the z-average size, or z-average hydrodynamic size, which I'll warn you is a little bit different from the z-average radius gyration used in polymer work. So in particle analysis work and DLS, we have kind of one definition of z-average I'm talking about here. It's different from what you'll find with doing Zim plots and the like from polymers. You also have a polydispersity, which is this second Fourier coefficient divided by the square of that initial decay constant gamma bar. And that's a measure of the width of the size distribution. So what is z-average? It's really the size determined from an intensity-weighted diffusion coefficient. And so, of course, the diffusion coefficient goes by 1 over diameter. And you stare at it for a while, you realize that the compact statement is that the intensity-weighted harmonic mean size. So 1 over the z-average, the sum of the diameters times the scatterings divided by the scatterings. So as size goes up, so does dz. Okay, so back to example, silica. So this is somewhat larger silicon I showed you before. The z-average diameter average is 480 nanometers, and the range of z-average that you get in the repeats is quite narrow. It's 473 is the low, 487 is the high. So it's 8 parts in 400, so it's about 2%. The polydispersity index is 0.08, and the range is 0.04 to about 0.13. And so you can see, so that's 0.04 out of 0.08, that's kind of 50% maximum. And the point here is that the measured polydispersity index tends to wander around more than the measured z-average diameter. And this kind of makes sense. You're doing a series of quadratic fits, and that quadratic term is just a little harder to get right than the z-average. The nice thing about z-average sizes is that they're numerically stable. Kind of, you set this up and you do the fit, and even if you throw a little noise at the problem, you always get the same answer. But there is more you can do, particularly in the R&D environment. If I make some autocorrelation functions, so on the left, I show a large particle and a small particle, and large is in green, small in red, and I make the mixture, you can see how the curve has a softening to it. Okay, so it's a mixture of this and all the intermediate sizes. And you can do a similar game with larger particles where you see how the curve has less of a slope than you see with single particle sizes. So I can stare at the math and figure out what's going on here, and eventually get myself around to an equation where I say that this autocorrelation function is really a sum of exponentials weighted by the scattering from each species. So if I have this, you say, oh, that's a Laplace transform. I take my data, I invert the Laplace transform, solving for S at gamma, and then I can eventually use some scattering factors and get myself to a size distribution. So in practice, here's an example. I take some 20 nanometer and 500 nanometer latex. I make two separate measurements. So these are different suspensions, and my 20 is in green, and my 500 is in blue, and the peaks are exactly where I expect them to be at 20 and 500. So I get pretty nice looking sets of data. I take my two buckets of sample, and I mix them together, and I get the curve in black after applying the inverse Laplace transform approach. And we do stabilize the problem for those of you who are into the math. And you'll see that the peaks have shifted by a little bit and the areas have shifted by a little bit, but we can really start to resolve particularly widely spaced particle sizes. So that's the good news. The kind of difficult news is that I mentioned we stabilize the problem. And so there are a lot of numerical tricks we use, because if you go to a mathematician, you say, here, I have a finite data set. Can you make me an inverse Laplace transform? And the mathematician's very accommodating. He says, you give me a finite data set, not only will I give you one valid inverse, I will give you an infinite number of valid inverse Laplace transforms. Well, that's a bit overly generous, because I really want one answer. Somewhat more practical people will say, well, we can't have negative scattering, so you've knocked out a huge fraction of those infinite cases. And then we have a few other comments about what we think about the size distribution, and you start drilling yourself down into kind of a reasonable answer, which would really be this black curve I show. But the reason the peaks are shifted are kind of back to that mathematician being just generous enough to give me an infinite number of size distributions that fit my data. So here's some examples. An example of colloidal silica. I actually showed this in my opening slide on laser diffraction, except this is done by dynamic light scattering. Might be a slightly different grade. It's a very similar material anyway. So this is about 30 odd nanometers. It's pushing 40. And it does, for that particular series of measurements, it does match our laser diffraction results. Colloidal silica is made by the truckload, used for all sorts of things. Clarifying beer, wine, and juice is one example of an application. Another example of what you can do with this technique, here I'm looking really at a large molecule, BSA, bovine serum albumin, and I can find the size. And I mentioned BSA because one of the things it likes to do is aggregate. If you look at it funny, it will aggregate. You can see it by GPC, and you can see it by dynamic light scattering, which is kind of a long-winded way of pointing out that you can use dynamic light scattering to look at small amounts of protein aggregation. And there's a comment in the slide. Here's an example where we are looking at dynamic light scattering as a function of time. So I kind of had that comment in the beginning that dynamic light scattering is a measurement on a microsecond time scale. And here we're looking at times of many, many hours. So let's see, 100 out, 3,000, 30,000. I guess it's a kilo, yeah, it would be about a kilosecond time scale or so. So repeating the measurement over kilosecond time scales and watching aggregation happen in lysozyme. It was basically destabilized at pH 2. I'm going to mention I also did a similar measurement with the view sizer. And the nice thing about the view sizer, I can start using the view sizer to nanoparticle tracking analysis. So that's really Sean's talk. That's going to help you understand what's happening up here with the larger particle sizes. Another application, which is liposomes. They're used, say, for targeting tumor growth. And if you're, say, delivering drugs for drug delivery, you might put them inside a liposome and then put it into the body. They remain stable over time. Another example application more recently of liposomes has been some adjuvant formulations for vaccines. And vaccines are certainly a hot topic these days. And so you can use either DLS or nanoparticle tracking to analyze them. Okay, we now move into method development. So the comment on method development is that this is probably where the action is going to happen. So I'm going to comment on dust. So they're generally large, rare particles in the sample. They're not really part of the sample. So if you have enough large particles in your sample, that's what you have. So anyway, then you're analyzing it. If you just have a few, that's not really what you want to look at, and you also get poor statistics, which messes up the DLS results. So in this case, filters are your friend. I'm gonna have to say over the decades that the water I see in laboratories has just gotten cleaner and cleaner, and so there's less and less work cleaning things up on everything, and I think that's driven by filtration sterilization in the pharma industry. So if you have a sample and you have some large particles you don't like, you can use a filter to take them out. If your particles are too large, and I'll give kind of a concrete example that comes up all the time, when I check an analyzer, I'll use 100 nanometer polystyrene latex. And so what I'll do is I'll filter the diluent, which is generally 10 millimolar salt, aqueous, through a 100 nanometer filter or 200 nanometer filter. I don't want to use such a small pore size while my analyte is about that same size. I have colleagues who will filter the entire suspension through a 1 micron filter. Well, you pick your poison, I guess. You can get filters in sizes from about 20 nanometers to 2 microns and on up, but up to 2 microns is what's relevant for our work. You can also centrifuge a sample and extract the supernatant. So yes, extract the supernatant because basically your large particles are going to sit in the pellet. That's another approach for cleaning samples. It doesn't require filtration. You got to be a little careful with filters because you don't want to filter your analyte. So going back to my example, if I had 100 nanometer sample, I used a 20 nanometer filter, my data is going to be terrible because it's all there's no particles, no scattering, nothing to look at, all noise. All right, suspension liquid. So dynamic light scattering is pretty kind to you about suspension liquids. I mean, I guess kind of one obvious constraint is you can't use a gas because the viscosity is so low, the time scale is too short. But you can use most liquids. You want to pick something that does not dissolve the particles and pick something that avoids loose agglomerates. You may wind up adding liquid to break up loose agglomerates. Adding energy to break up loose agglomerates. And that can be anything from just stirring a little bit to ultrasound to lots and lots of ultrasound milling your particles, which may not be a good idea. The most popular liquid is water. So any aqueous suspension is people like a lot. Don't forget about organic solvents. Of course, you do need to worry about the expense, disposal, and other hazards, which is why water is so popular, but keep that in mind as an option. Surfactants, so I get some water. I don't quite like how the water is affecting my particles. And so if I can add something like tetrasodium pyrophosphate or Triton X in order to ensure the particles are wetted and stay separated, that will be a lot more fun than spending the next couple of years doing everything in THF, for example. So wetting. A lot of dry particles don't really like to form nanoparticle suspensions without a lot of effort. And that's because they have this immense surface area and surface energy rules. So you can make a test of a candidate surfactant. And so you see two zoomed in pictures on the left and the right. And I'm going to sprinkle just a tiny, tiny amount of particles on the top. If the particles sit on the top like they do here, and they're not going through the surface tension of the water, that's a really bad sign. That usually means that your particles are not being wetted and you're going to have just an awful time. If the particles break through the surface and sink, they're either wetted because you picked the right chemistry, and that's great, or they're so big gravity is more important than surface tension. So if they're wetted, that's great, you're in luck with DLS. If the particles are just big, then you're going to talk to Julie about laser diffraction or others. And if you put too big a clump on, you will also see them burst through. So you have to just move the tiniest amount for this test. That said, it's a great test to just eyeball which of your surfactants are going to work with an unknown material. Here's my comment on solvents. Yeah, again, isopropyl alcohol. I mentioned THF, but isopropyl alcohol is more fun. And don't forget the hazards. If you have a system and you need to figure it out, quite often you'll want to take a series of beakers or scintillation vials and make a bunch of suspensions, adding a little tiny bit of particles to each, and look at them by eye and see which ones are going to be good for measurement and which ones aren't. And so if you see, I think the couple on the right, the particles just sat on top or clumped up. This one on the left, they kind of burst into a nice little cloud. And so I might pick that recipe. Sometimes you don't know you're going to have to do it. And sometimes you say, all right, let's try Triton-X. Spend 20 minutes on Triton-X. All right, let's try sodium phosphate, 20 minutes on sodium phosphate. And it can be easier to say, I have 7 surfactants. Let's make all the solutions, then make all the suspensions, and then look at what happened. And then eyeball them to decide what goes for further work. So we have our particles in suspension, and then we want to know, well, what concentration do I want to work at? Well, towards the end of the effort, you're going to make a plot like the one in the screen, where I plot measured z-average size as a function of particle concentration. Here I use ppm, but you can use any units. You can use level of dilution and so on. The key is I'm using a log scale here. I'm not making measurements at 1, 2, 3, 4, 5, all the way up to 1,000. I'm making measurements at 3, 20, if I did 30, 60, 100, 1,000. So I'm making fairly large steps here. And I can see that there's a flat spot where I'm pretty much getting the same size. If I go too low in concentration, then my result is pretty noisy. And if I go too high, as my concentration goes up, I'll start to see that the measured size is changing quite rapidly or relatively rapidly with concentration. And what's happening here as I go to higher concentrations is quite often we have particle-particle interactions. And one thing I didn't mention in the beginning is that all this math I showed you, we go through pretending that the particles do not interact with each other. We don't even like to think about them bouncing off each other, leave alone questions of long-range electrostatic interactions. And so the reason for that is because those particle interactions will affect particle motion, and that will affect your dynamic light scattering results, give you kind of oddball sizes. Before you make a pretty plot, you have to at least get some data. And so kind of the old rule of thumb is you make a sample, and can you read a newspaper through it? So there's a fellow reading a newspaper, but he has the sample coffee cup on the wrong side of the newspaper. A better graphic is on the right, where I have a series of cuvettes filled with suspension. And I can look and say, gee, the far left I can read through, the next I can. As we get to the middle, you can just read through it. And as you get to the right, you can't see anything, okay? So really the best range for this material is down on the left-hand side, where I can see letters. And this is how you find your starting point before you go back and make this sort of graph. Because you really don't want to start your graph somewhere on the far right that it is nowhere near where it's going to work. It's just too much effort. Or on the far left. So you can estimate your starting concentration range here. Quite often for applications work, this is the important first step. And when I know I can get some kind of civilized result with this test, I know that the application is quite likely to work, and it's just a matter of refinement. Now, I mentioned long-range electrostatic interactions, and later on we'll talk about zeta potential and what they mean and so on. Here I just want to talk about what they mean for dynamic light scattering. So this was colloidal silica, and I made it in 2 different ways. I diluted it in DI water, that's with the red line, and I also made a set of concentrations diluted in 10 millimolar NaCl, sodium chloride. Measured the apparent sizes with each. Now, the thing is that by adding salt, I've turned off or screened the electrostatic interactions. So the red is the case where the particles interact with each other strongly, and the blue is the case where they don't. But the optical effects of both are the same. So the overall particle concentration is the same between, say, this measurement and this measurement. They're a little off from dilutions, but yeah. So any multiple scattering effects affect both measurements equally. And what you see is that when I turn off the electrostatic interactions, my range of sizes where I get the same diameter becomes quite wide. It's about 1.5 decades where I'll have the same measured size for a sample with the salt and screened electrostatic interactions. But if I dilute in water, have the same optical effects, but different particle interactions, I can see that my measured size becomes a somewhat stronger function of the concentration. Now, the case in blue may be more desirable because it means that when you make a sample, you can be a lot sloppier about your dilutions, which leaves you more time to think about other critical measurements. Or you might decide, hey, you know what? It just isn't that critical where my size is, and there are applications like that. I'll just use DI because it's easier. So this is another thing to think about as you're developing a method, and particularly as you're going into quality control work where you need nice repeatable measurements for a very long time and across operators and so on. So kind of some summary on hints, if you will, for method development. I list web search in the summary just to remind you I didn't forget about it. I think everybody goes to Google these days, at least my kids do. So you'll probably start there, just look up DLS of whatever you're trying to measure. Think about your solvent and surfactant. Think about how much energy you need to add to get it dispersed. Expect to filter to make sure you don't have any large particle impurities. Then pick the largest cell, which I didn't really get into, but you can get various volumes of liquid. Generally, the smaller your liquid volume, the more hassle it is to deal with. And so if you can use the larger, less expensive cells and milliliters rather than microliters, it's just a whole lot more fun. And then optimize concentration or the concentration range for your measurement. Now, I kind of alluded to this briefly, and I want to talk about it a little bit more explicitly. Settling in DLS, not all motion is Brownian motion. So if you take a particle system, there's lots going on. You have thermal energy that likes to move the particles around. We have viscous drag and likes to slow them down. And then we also have gravity, which will either make a particle sink or rise, depending on the density of the particle, the density of the liquid, and the size of the particle. And so when you start getting larger particles, and I'd say about 1 micron or so, you're going to start to see fairly strong gravitational effects. And so I kind of have movement on a length scale for Brownian motion versus gravitational settling. We'll ignore a few kind of wild assumptions in there. It says around 1 micron is where both motions are about the same order of magnitude. And what that means for the analyst is that measuring about 1 micron gets to be a real hassle by dynamic light scattering. And I tend to discourage it. Even though the analyzer can go up to many, many microns, you're just going to have a whole lot more fun with laser diffraction. Now, conversely, as you move down to the very smallest particle sizes, DLS really comes into its own, and it's the only tool you like. So that's kind of your natural limit for dynamic light scattering. Now, there's some tricks, but that's something to think about as you choose analyzers or choose techniques. So DLS disadvantages. One is it's sensitive to large particles. If you add a few large particles to your sample, then it's going to start affecting your results. And that's kind of where the filtration comes in. But if you have tails of your distribution that run up into the many micron size range, you can be in for a bad time. If you need details of your distribution, so how many particles are 10 nanometers versus 20 nanometers, DLS is probably not really your friend. You're looking at nanoparticle tracking for that. And it's not really appropriate where settling is significant. And I point people towards laser diffraction for that. Because of the different technique, you can actually use stirrers to keep the samples up in suspension and in the measurement measurement area volume. And so that just makes the whole measurement a lot more rational. Now, the advantage of dynamic light scattering, it's non-invasive. You get your sample back. You just shine a little bit of light on it. It requires only small amounts of material. So you can go as small as 10 microliters of sample volume. It's good for detecting trace amounts of aggregate. So if you're looking for, say, BSA monomer dimer, DLS is your friend, or any other kind of initial onset of protein aggregation. It's good for macromolecular sizing. You can get down to almost oligomer type sizes with dynamic light scattering, if that's what you need to do. And it really gets to the smallest particle sizes compared to other sizing techniques. I'm going to add it's quite repeatable and quite fast compared to other techniques in this size range. If you're in the market, we have our SZ100 and it's a single unit that says size, data potential, and molecular weight measurements. So you can reach out to us through email, and we'll give you more details. So kind of a summary, and I'll leave this up. DLS gives you fast, repeatable nanoparticle sizing. Think about your suspension chemistry method development. You're in the regime of nanoparticles, and these chemistry questions start becoming real interesting. What are my interactions between particles? How can I get them to where they need to be just to make the measurement? The mercy in it, of course, is that I need a suspension that works for half an hour. And people who do formulations commercially think in terms of months of stability. I just don't worry that much. And remember, this reports hydrodynamic size of your particles, okay? And so you kind of remember these three things, you'll have the key takeaways. And I think it is time for questions.
Well, thank you, Jeff, for the amazing webinar. We have quite a bit of questions, so let's get through it. First question that came in early on is, what technique is best for measuring nanobubbles?
Okay. It depends on what you want to measure. So you can use both. You can use both dynamic light scattering or nanoparticle tracking analysis. And if you need nanoparticle concentration, nanobubble concentration, I will probably point you towards nanoparticle tracking analysis because DLS just doesn't do concentration particularly well. If you need your average size, then I would point you towards dynamic light scattering. It's a less expensive technique. So kind of the follow-on for that is, what do you need to learn about your nanobubbles? And I guess I get to cheat because I have both in my lab, so we can run both and decide which works for somebody. Yeah. So anyway, there's an answer: nanoparticle tracking or DLS, depending.
Thank you. How are polydispersed sample handled in a meaningful way? And this is sort of a three-part question. And what physical chemical parameters are required, and how are they obtained?
Okay, so I guess the word meaningful, I'm sure, is important somehow. So dynamic light scattering, the approach I recommend for DLS, for polydispersed samples, is that you look at the width of the size distribution, or what's called the polydispersity index. And that's a kind of a complicated number to unpack. It's really only the number a scattering person will enjoy, but the polydispersity index does go up as your sample distribution becomes wider. If you need to use inverse Laplace transform, then you'll have probably intense size as a function of intensity for each species. You might decide to use the scattering, which comes from the known refractive index of the particles. And here known means that you, the operator, has entered in the correct refractive index of the particle and the liquid. And then we can calculate back to find the volume of particles at each size, go a step further back and get the number of particles at each size, and then kind of worry at each step of the way as we move further and further away from the raw data. If you have very broad distributions, or you need to really get at the details, nanoparticle tracking analysis might be a better approach. Yeah, so I went through what he'd need, which is refractive index. I went through what we do in DLS and some comments on what to do if that doesn't suffice. Okay, I think I'm set.
Thank you. Yes, thank you. Okay, the next question. If you are working with proteins, how do these electrostatic interactions affect the results? And then part two of that question is, what is the size limit?
Okay, so if you're working with proteins, generally the electrostatic interactions come at you real early because most protein solutions do not like being in DI water, in low salt liquids. And most protein solutions really like to have something like PBS. And because you've dissolved your protein in something like PBS, phosphate buffered saline, or even physiological saline, you have so much salt in there, you have screened the electrostatic interactions quite effectively. And so you can just go ahead and ignore them for the purposes of sizing. Now, there is another effect in proteins, which would be that a lot of them are amphoteric, and as I change pH, I will change the surface charge. And so you can modify your charge using pH, and that will modify your suspension stability, and that will in turn modify your DLS results. In that case, you're really using DLS to track what's happening to your protein as you change conditions. So I don't worry too much about charge in terms of measurement with proteins because I very rarely see them in DI water. I do worry about charge and everything else when I'm trying to make sure I'm measuring the right sample. And that is the aggregation state that you're interested in.
Thank you. Okay, the next question is a two-part question as well. What is the role of PDI? If we get high PDI, what does that mean? And the part two of the question is there an upper PDI at which the data would not be accurate?
Okay, so a larger PDI means your size distribution is broader. If you have a very narrowly distributed sample, you'll see PDIs and they're quite small. So that's kind of role in PDI interpretation. An old rule was if the PDI was more than about 0.3, you would say that polydispersity effects are strong and cumulus analysis is going to get a little questionable. And then you might look at the size distribution or switch over to nanoparticle tracking analysis. Comment on that rule is it depends a little bit on your goals. And you might decide that some of your goals are sufficiently met by DLS. You don't need to go to nanoparticle tracking and multi-laser nanoparticle tracking, or you might decide that's the way to go. So yeah, okay, I hope that answered. If you're seeing over 0.3, you're probably starting to think about other techniques if width of distribution is very important to you.
Thank you. Okay, how to correlate DH with particle size obtained by other techniques, such as laser diffraction, imaging, etc.
Okay, yeah, so the first comment is that if your results are within 10 to 20% of each other, you declare victory and go home. So that's just kind of the first thing to get in your mind is you don't, the second thing to get in your mind is if they overlay exactly, you're either working with perfect spheres or someone is, or something has gone wrong. So just a perfect correlation would be unexpected, to say it mildly. You'll have to think about the physics of each measurement. And so this goes back to my comment on core shell particles. If you look at DLS versus electron microscopy, you might say, hey, wait a minute, I know this is a core shell, I just don't see part of it in my micrograph, and that explains the difference. More often, you'll start thinking about questions of particle shape and saying, well, my TEM shows a football shape or a squiggle with a size in the range of 100 nanometers. Say it's called, pretend the squiggle length is 150. And my DLS shows a hydrodynamic size of 80 nanometers. Okay, that's close enough. Let's go home. Of course, if your DLS shows 2 nanometers, then you got to worry. Your laser diffraction is looking at how something scatters compared to how something moves. And so that's yet another measure of size. And once again, if you're in the same neighborhood, you smile and move on. And if you are getting different answers, then you really need to investigate the physics of each measurement to figure out why. And that's going to be very particle dependent. So this whole core shell argument does not matter if you're just looking at, say, a liposome, because a liposome isn't going to have a very electron dense region like a metal compared to non-electron dense region in the imaging, say freeze fracture or something like that.
Thank you. Okay, so this question, how does it work with small and big particles with bubbles inside? Do bubbles give effect on the data?
Okay, so all right, so I'll answer the question two ways. One is imagine two particles and the particles have bubbles inside the particles. So I'm thinking of a magic, I can think of some larger fine particles that are actually you can have air inside them and then a hard shell and then liquid around that. So I'm imagining that on a nanoscale. That wouldn't really affect your results, except unless you make the particle particularly buoyant and gravity comes up and gets you. So if there are bubbles inside the particle, then it doesn't change the hydrodynamic size of the particle, and so I ignore them. Now let's take the other case, which is I have a suspension with nanobubbles, like someone else asked about earlier, plus some bonus nanoparticles, let's say some polystyrene just for fun. Then I can't tell the difference. So I will just report this average size of everything in that mixture, or the size distribution of everything in that mixture, and I won't be able to tell you what's a bubble and what is not.
Thank you. All right, so this one, for one of my samples, NTA and DOS, they're given different results. NTA is around 130 nanometers, whereas DOS is 450. Should I look at microscopy to confirm either DOS or NTA?
I mean, that's a big difference. That's a huge difference in sizes. I mean, I've taken NTA results, converted them to correlation functions and back to DLS and matched them up on our analyzers. Yeah, one thing could be, there are a couple of things. One is if you have a single laser NTA, you're going to have trouble with a wide range of sizes in the same sample. And that may be why you're missing the large particles in the suspension. Another is that you have to remember that DLS is going to be weighted by the scattering intensity, which goes up strongly with particle size. So if you have a 150 nanometer in your NTA, but you have a tail in your size distribution stretching out to 450, or well, more like 500, then that may explain the results. Yeah, something is odd about that results set. Yeah, you're going to have to use something to confirm them. Conventional microscopy won't work at those sizes. I mean, it will work at 450, but you'll never see the 130s. Anyway, yes, you got to do something. It's a good question. I can't answer with the information in front of me. Sorry.
Yeah, we probably need more details.
Yeah.
And I also had to skip through some of the questions that also came in later. For those people who haven't had their questions answered, please go ahead and email us at labinfo@hariba.com. Thank you so much for your time today, Jeff.
Well, thank you everybody for coming out and listening and asking some interesting questions. Look forward to corresponding with some of you. Okay.
For sure. So for now, have a great day, and we'll see you at one or more of our future webinars. Thank you, everybody.
Thanks all.
Bye.
Bye-bye.